Good day, everyone. Today, I will be sharing to you the history of number theory. Number theory, or in older usage, arithmetic, is a branch of pure mathematics devoted primarily to the study of the integers. It is sometimes called the Queen of Mathematics because of its foundational place in the discipline. Integers can be considered either in themselves or as solutions to equations. Questions in number theory are often best understood through the study of analytical objects that encode properties of the integers, primes, or other number-theoretic objects in some fashion. The older term for number theory is arithmetic. By the early 20th century, it had been superseded by number theory. And now let's come to the history of number theory. The early number system and symbols. Primitive counting. Anthropologists tell us that there has hardly been a culture, however primitive, that has not had some awareness of number, though it might have been as rudimentary as the distinction between 1 and 2. South American Indians ventured farther than the Aborigines in being able to count their counting vocabulary. 3 was called 2-1, 4 was 2-2, and so on. A similar system has been reported for the Bushmen of South Africa who counted to 10. 10 is equal to 2 plus 2 plus 2 plus 2 plus 2, with just 2 words. Beyond 10, the descriptive phrases became too long. The earliest and most immediate technique for visibly expressing the idea of number is tallying. The idea in tallying is to match the collection to be counted with some easily employed set of objects. These were fingers, shells, or stones. Mayan numeration system. The Mayan calendar year was composed of 365 days divided into 18 months of 20 days each, with a residual period of 5 days. This led to the adoption of a counting system based on 20, a vigesimal system. Numbers were expressed symbolically in 2 forms. A short horizontal bar represented 5 and a dot 1. For example, number 6. There is 1 horizontal bar and 1 dot. Number recording of the Egyptians and Greeks. Hieroglyphic representation of numbers. Egyptian system was a decimal one, from the Latin decem, which means 10, which used counting by powers of 10. Egyptian method of writing numbers was not a positional system, a system in which one and the same symbol has a different significance depending on its position in the numerical representation. Let us look at the figure. Example, number 1 is represented by a short vertical line. Egyptian hieratic numeration. In this so-called hieratic or sacred script, the symbols were written in a cursive or free-running hand so that at the first sight, their forms bore little resemblance to the old hieroglyphs. Numerical representation was still additive based on powers of 10. But the repetitive principle of hieroglyphics was replaced by the device of using a single mark to represent a collection of like symbols. Let us look at the figure. Example, number 4 is represented by a short horizontal line. The Greek alphabetic numeral system. Around the 5th century BC, the Greeks of Ionia also developed a ciphered numeral system, but with a more extensive set of symbols to be memorized. They cipher their numbers by means of 24 letters of the ordinary Greek alphabet, augmented by 3 obsolete Phoenician letters, the Digamma for 6, the Kappa for 90, and the Sampi for 900. Look at the figure. For example, number 1 is represented by the Greek alphabet symbol alpha. Number recording of the Babylonians. Babylonian cuneiform script. Shortly after 3000 BC, the Babylonians developed a system of writing from pictographs, a kind of picture writing much like hieroglyphics. Babylonians used first a reed, later a stylus with a triangular end. The sharp edge of a stylus made a vertical stroke, and the base made a more or less deep impression, so that the combined effect was a head and tail figure resembling a wedge, or nail. Because the Latin word for wedge is cuneus, the resulting style of writing has become known as cuneiform. The Babylonian positional number system. The Babylonian scale of enumeration was not decimal, but sexagesimal, which means 60 as a base, so that every place a digit is moved to the left increases its value by a factor of 60. When whole numbers are represented in the sexagesimal system, the last space is reserved for the numbers from 1 to 59. The next to last space for the multiples of 60, preceded by multiples of 60 squared, and so on. Writing in ancient China. Let us look at the figure for the writings of the Chinese. For example, number 10 is represented by a figure forming a cross. Dawn of Arithmetic. From the Egyptian Arithmetic. The Egyptian arithmetic was essentially additive, meaning that its tendency was to reduce multiplication and division to repeated additions. Multiplication of two numbers was accomplished by successively doubling one of the numbers, and then adding the appropriate duplications to form the product. To find the product of 19 and 71, for instance, assume the multiplicand to be 71. Doubling thus, 1 plus 1 is 2, 2 plus 2 is 4, and so on. And on the other side, 71 plus 71 is 142, 142 plus 142 is 284, and so on. Here we stop doubling, for a further step would give a multiplier of 71 that is larger than 19, because 19 is equal to 1 plus 2 plus 16. Let us put checks alongside these multipliers to indicate that they should be added. The problem 19 times 71 would then look like this. There are checks along 1, 2, and 16. Adding those numbers in the right-hand column opposite the checks, the Egyptian mathematician would get the required answer 1349. That is, 1349 is equal to 71 plus 142 plus 1136 is equal to the quantity of 1 plus 2 plus 16 times 71, or simply 19 times 71. Babylonian Mathematics. In mathematics, the Babylonians were somewhat more advanced than the Egyptians. Their mathematical notation was positional but sexagesimal. They used no zero, they could extract square roots, they could solve linear systems, they worked with Pythagorean triples, and they solved cubic equations with the help of tables. The first historical find of an arithmetical nature is a fragment of a table. The broken clay tablet, Plimpton 322, found in Larsa, Mesopotamia, about 1800 BCE, contains a list of Pythagorean triples, such as integers 3, 4, 5. The heading over the first column reads, "The tachyltum of the diagonal which has been subtracted such that the width is..." Euclid's Book 9, Problems 21 to 34, is very probably Pythagorean. It is very simple material. Odd times even is even. If an odd number measures an even number, then it also measures half of it. But it is all that is needed to prove that it is irrational. Classical Greece and the early Hellenistic period. Aside from a few fragments, the mathematics of classical Greece is known to us either through the reports of contemporary non-mathematicians or through mathematical works from the early Hellenistic period. In the case of number theory, this means, by and large, Plato and Euclid respectively. Plato had a keen interest in mathematics, and distinguished clearly between arithmetic and calculation. By arithmetic, he meant, in part, theorizing on number rather than what arithmetic or number theory have come to mean. Theaetetus was like Plato, a disciple of Theodorus. He worked on distinguishing different kinds of incommensurables and was thus arguably a pioneer in the study of number systems. Euclid devoted part of his Elements to prime numbers and divisibility, topics that belong unambiguously to number theory and are basic to it. In particular, he gave an algorithm for computing the greatest common divisor of two numbers, or the Euclidean algorithm, and the first known proof of the infinitude of primes. Pythagoras' famous theorem states that the sum of the square of the shorter sides of a right triangle is equal to the square of the longer side, which is the hypotenuse. He also worked on proving various other theorems or axioms, including that the square root of 2, which is an irrational number, could not be given in the form of an integer or fraction. He also discovered that 28 was a perfect number. Very little is known about Diophantus of Alexandria. 6 out of the 13 books of Diophantus's Arithmetica survive in the original Greek. 4 more books survive in an Arabic translation. The Arithmetica is a collection of worked-out problems where the task is invariably to find rational solutions to a system of polynomial equations. Thus, nowadays, we speak of Diophantine equations when we speak of polynomial equations to which rational or integer solutions must be found. While Diophantus was concerned largely with rational solutions, he assumed some results on integer numbers, in particular that every integer is the sum of 4 squares. Aryabhata showed that pairs of simultaneous congruences could be solved by a method he called Kutaka or pulverizer. This is a procedure close to the Euclidean algorithm, which was probably discovered independently in India. Brahmagupta started a systematic study of indefinite quadratic equations. Later, Sanskrit authors would follow using Brahmagupta's technical terminology. A general procedure, the Chakravala or cyclic method for solving Pell's equation, was finally found by Jayadeva. Arithmetic in the Islamic Golden Age. In the early 9th century, the Caliph Al-Mamun ordered translations of many Greek mathematical works and at least one Sanskrit work. Diophantus's Arithmetica was translated into Arabic by Kusta ibn Luka. According to Rashid Rushdi, Al-Karaji's contemporary Ibn al-Haytham knew what would later be called Wilson's theorem. Western Europe in the Middle Ages. Other than a treatise on squares in arithmetic progression by Fibonacci, no number theory to speak of was done in Western Europe during the Middle Ages. Matters started to change in Europe in the late Renaissance, thanks to a renewed study of the works of Greek antiquity. The early modern number theory. Pierre de Fermat, the prince of amateurs, a certain French civil servant, was the last greatest mathematician to pursue the subject as a sideline to a non-scientific career. He did make repeated use of mathematical induction, introducing the method of indefinite descent. One of Fermat's first interests was perfect numbers and amicable numbers. This led him to work on integer divisors, which were from the beginning among the subjects of the correspondence that put him in touch with the mathematical community of the day. Fermat's achievements in arithmetic include Fermat's little theorem, stating that if p is a prime and a is any integer not divisible by p, then a to the power of p minus 1 is divisible by p. Fermat asserted that if n is greater than 2, then the Diophantine equation x to the power of n plus y to the power of n equals z to the power of n had no solution in the integers except for the trivial solutions in which z is equal to x or z is equal to y, with the remaining variable being 0. This is known as Fermat's last theorem, or more accurately, Fermat's conjecture. The interest of great Swiss mathematician Leonhard Euler in number theory was first spurred in 1729, which has been called the rebirth of modern number theory, after Fermat's relative lack of success in getting his contemporaries' attention for the subject. Euler's work on number theory includes the following. First, he gave his approval for using the Greek letter pi for the ratio between the circumference and the diameter of a circle, and e to represent the base of natural logarithms. Second, proofs for Fermat's statements. This includes Fermat's little theorem, generalized by Euler to non-prime moduli. Initial work towards a proof that every integer is the sum of 4 squares. Third, first steps towards analytical number theory. In his work of sums of 4 squares, partitions, pentagonal numbers, and the distribution of prime numbers, Euler pioneered the use of what can be seen as analysis in number theory. Since he lived before the development of complex analysis, most of his work is restricted to the formal manipulation of power series. He did, however, do some very notable early work on what would later be called the Riemann zeta function. And lastly, fourth, quadratic forms. Following Fermat's lead, Euler did further research in the question of which primes prefigure quadratic reciprocity. Joseph Louis Lagrange, Italian by birth, German by adoption, and French by choice, was the first to give full proofs of some of Fermat's and Euler's work and observations. For instance, the four-square theorem and the basic theory of misnamed Pell's equation. He also studied quadratic forms in full generality. His most prominent influence was his contribution to the metric system and his addition of a decimal base, which is in place largely due to his plan. Some refer to Lagrange as the founder of the metric system. The Lagrangian polynomial is the far easiest way to find the curve through points. Adrien-Marie Legendre, a French mathematician, was the first to state the law of quadratic reciprocity. He also conjectured what amounts to the prime number theorem and the Dirichlet's theorem or arithmetic progression. He gave a full treatment of the equation and worked in quadratic forms along the lines later developed fully by Gauss. In his old age, he was the first to prove Fermat's last theorem. The greatest mathematician of modern times, Carl Friedrich Gauss, was so very German that never in his life did he leave the country, not even for a visit. During his student days at Caroline College, Gauss formulated the method of least squares, by which the most likely value of a variable quantity could be estimated from many random observations. In his Disquisitiones Arithmeticae, Carl Friedrich Gauss proved the law of quadratic reciprocity and developed the theory of quadratic forms. He also introduced some basic notation and devoted a section to computational matters, including primality tests. The last section of the Disquisitiones established a link between roots of unity and number theory. Gauss was the last complete mathematician, and it is no exaggeration to say that he was in some degree connected with nearly every aspect of the subject. His contemporaries regarded him as Princeps Mathematicorum, or the Prince of Mathematicians, on a par with Archimedes and Isaac Newton. He proved what is now known as the fundamental theorem of algebra. Gustav Peter Lejeune Dirichlet was one of the most gifted German mathematicians in the generation after Gauss. Although his interests covered many areas, he devoted himself primarily to the study of numbers. In 1837, Dirichlet established the remarkable theorem that goes by his name today. This result of the existence of prime numbers in a given arithmetic progression had been conjectured by Legendre, who tried to give a proof but failed. The first use of analytic ideas in number theory actually goes back to Euler, who used formal power series and non-rigorous limiting arguments. The use of complex analysis in number theory comes later. The work of Bernard Riemann on the zeta function is the canonical starting point. Jacobi's four-square theorem, which predates it, belongs to an initially different strand that has by now taken a leading role in analytic number theory, or modular forms. And now let's come to the recent approaches and subfields of number theory. First is probabilistic number theory, which can be seen as an important special case of study of variables that are almost but not quite mutually independent. For example, the event that a random integer between 1 and a million be divisible by 2 and the event that it be divisible by 3 are almost independent but not quite. Second, arithmetic combinatorics. Arithmetic combinatorics is a presently coalescing field. It subsumes additive number theory. It focuses on issues of growth and distribution accounts in part for its developing links with ergodic theory, finite group theory, model theory, and other fields. Most areas of mathematics go from inception to maturity within at most a century. But in number theory, there are questions that were formulated more than 2,000 years ago, such as whether any odd perfect numbers exist, that have still not been answered. Of the principles that have been established in number theory, a great many were first revealed by explicit experiments. From its inception in classical times through its development in the 1600s and 1800s, number theory was largely separate from other fields of mathematics. But starting at the end of 1800s, increasing connections were found to other areas of both continuous and discrete mathematics. Properties of numbers and certain elementary aspects of number theory have also always played the central role in amateur and recreational mathematics. And that's the history of number theory. I am hoping that you've learned a lot from the points I've shared. This is Alcher Huwagpaw HArpi Learning. Thank you and good day.